So good afternoon to everyone. I hope you had a nice conference so far. For me, it's a very big pleasure to present to you, as my first international presentation was actually exactly 9 years ago in OWASP Europe. So it's a nice closure. As mentioned, I've been practicing a lot of web application security work in the past, but in the past 4 years, I've been mainly focused on mobile security as part of our work in SecEU to identify and block attacks against mobile devices. So we do a lot of work around network attacks, malicious apps, and vulnerabilities. But today, what I want to touch is actually the evolution of mobile malware. In very short, what I plan to do is to give you the evolution that we see in malware and the kind of things they are targeting, the attackers. I'm going to discuss an example that we recently uncovered about how simple malicious app can actually circumvent app sandboxing in Android without rooting the device. So we will have a section about that. And later on, we will discuss about the classical technologies to analyze applications to try to identify maliciousness and the variety of techniques in which it is possible to bypass them. And I also plan, assuming the demo works as expected, to build on stage an example of such malicious app. So that's in very short. So let's start. So I want to start with something that I remember as a young boy, and that was my first virus that I ever saw. I believe some of you also remember that. It was around 88. So those of you that are raising your hands, it indicates that you're not very, very young. And what I remember when I was seeing this is that this was an inconvenience for me as a user. And over there, what we have seen is that this kind of capabilities by malicious writers have been translated in order to attack organizations and steal money. And like 24 years later, we started to see major attacks coming between countries, right? Stuxnet, or that example from last December, where by many, based on many research, it was actually an attack coming from Russia against Ukraine. So this is a very, very interesting trend that we've seen over the years in classical malware in desktops. But what we're seeing in mobility is the same kind of evolution, but it's just moving much, much faster. Like a few years ago, I remember Android malware that was mainly an inconvenience. But if you look at the news in the past year, what you may see is that you suddenly see ransom. You see attacks on banks that circumvent two-factor authentication. You're seeing many, many attacks. And this kind of evolution is actually, in our perspective, moving very, very fast in order to target organizations through mobile devices. And I think that the reason is very, very obvious, right? If you think about a mobile computer, a mobile device, in comparison to a classical computer in the organization, it has access to data, it has access to services, the classical things that one would try to hijack. But it's also the ideal tracking device ever invented, right? It's with us all the time, almost all the time, turned on, and the meaning of a malicious app running on that device is actually being able to track what you're doing 24/7, who you meet with, and actually what you say when you're sure that nobody is listening. So this is obviously great motivation for attackers, and especially malicious apps writers. On the other side, there are very good things that happened in mobility, especially around mobile operating systems, right? Most of the applications that we consume are coming from the public stores. There are many, many technologies that Apple and Google has in order to mitigate the risk of malicious apps. So it's a challenge of distribution for attackers, right? The second element is that we are seeing a lot of attempts to make malware more aggressive, and in some cases, doing so requires the victim to do unnatural things. We're used to just download an app and run it. When we do something else, it might be more challenging for the attacker to convince us to do it. So I want to give you a few examples from the past year about the kind of attacks we're seeing in the wild around mobile malware. And I want to start with iOS, as in the past it was perceived as not likely target for malicious apps. And we've seen many, many campaigns over the 9 last months that affected millions of iOS users, including non-jailbroken devices users. So Xcode Ghost, how many of you know that attack? Okay, so this is actually a pretty interesting example, as this is a sophisticated attack that was conducted. The story was that the attackers wanted to make sure that they managed to insert malicious apps into the public Apple Store. So what they did is they started to distribute a fake version of Xcode, the IDE for Objective-C, for development of iOS. And it was originated from Baidu, by the way. And then there were many, many major developers that started to use the fake version of Xcode. So they were generating their very popular apps, including WeChat, for example, which is used by hundreds of millions of users. And they just submitted the new versions of their apps to the App Store, as they do every few weeks. But this time, because of the fake IDE, the IDE inserted into their legitimate apps malicious logic. So it got into Apple. Apple trusted the apps because it was legitimate and well-trusted developers. And then a huge amount of people just downloaded malicious apps from Apple Store. So it's one interesting campaign that was uncovered. The second one came a bit later, and that's eSpectre. It's an interesting example since, again, it affected jailbroken and non-jailbroken devices. And the interesting part is that in this case, the malicious apps did not arrive from the public store, but instead from a side-loaded technique. In this case, they used enterprise development certificates in order to install malicious apps without having Apple review it, because it came from the outside. They did a lot of cool things, but one of the interesting stuff that happened is that because it did not arrive from the Apple Store, they were able to use a lot of APIs that are regularly not approved by Apple in order to make their malicious apps much more aggressive. Install apps, hide apps, hijack execution of apps, etc. So this is iOS. There are actually a lot of other examples coming recently. But I want to talk also about Android, because if you think about the evolution of Android malware, a few years ago, 5 years ago, you could find a huge amount of malicious apps in Google Play. But over the years, Google have done a great job of using technologies like Bouncer and Verify apps, and the number of malicious apps in Google Play became much, much smaller. But malicious writers do not just stop. The trend that has started and today is very major is that most malware is actually coming from third-party stores, meaning not from Google Play, but instead from other sources. And that has actually generated two interesting trends. First one is the problem of repackaged apps. And we will discuss this later on today, including a live demonstration of the problem. And the second element was that attackers try and continue to try to make their apps much more aggressive and powerful. And I want to share with you the challenge I mentioned to you. A few months ago, we started to look at the following challenge. We wanted to be able to create a malicious app that does not root the device, but yet can see whatever you're doing on your device in other apps, right? And even if possible, execute commands on the victim's behalf in other apps. And in a nutshell, this does not make sense, as the whole notion of mobile operating systems relies on app sandboxing, right? One app cannot really influence or see what other apps are doing on your device. That's why I let your children maybe download games from many sources, but yet you go to your bank and email and corporate resources in the same device. It's separated. And the challenge was actually to circumvent that. We quickly thought about a kind of capability that every time it is introduced in the operating system, it leads to problems. And that's obviously accessibility capabilities. Okay? Accessibility capabilities means things that make limited people, like people that don't see well, maybe hear what they're watching on the screen. So these kind of capabilities that over the years have led to many, many security issues in Android are actually extremely powerful. So for those of you, by the way, how many users of Android do we have here? Okay, nice. I can see that I'm in Europe, not in the US, so it's nice. So these capabilities actually allow a dedicated app that uses these capabilities to be able to watch what's happening on your device, and then just like talk what you're seeing, right? So this capability can also allow someone to perform actions on other apps. So it's very, very powerful, very valuable to impaired people, but obviously very, very valuable to attackers as well. And the Android developers obviously understood that, and for that reason, they created a mechanism that is extremely cumbersome to allow a given new app to get these very powerful capabilities. I just want to play this. This is the recording of the process that you as a user has to do in order to approve the accessibility capabilities to a new app, okay? So it's a very, very long process. You have to go to this accessibility dialog. You have to try to enable it. You have to see all of these warnings about what's going to happen. And for that reason, we've never seen a major malware campaign uses these capabilities, even though they're amazing. You can see what happens in other apps. You can perform actions in other apps. So that was the result. Yet we wanted to find a way to solve that, to create an app that will not require this process, but yet get these capabilities. And we were looking for a logical flaw, not for a specific implementation flaw. And then we looked at other very, very valuable capabilities in Android, and I specifically talk about the capability of draw over apps. So you know this from Facebook and other applications, that they can just draw on your screen new messages that arrive without waiting for you to open the app. And there is a pretty weird capability in this capability, and that's the ability to cover the screen whenever the app wants to, and also sets the cover in a way that if someone clicks on it, it does not get the click, but instead it propagates to the underlying layer. Okay? Now connect that with accessibility APIs together, and you suddenly see a logical flaw that is kind of terrible. And I want to show you an example of a POC we've created about that problem. So I will explain. You're seeing a game that we've created. It's not a good game, so don't laugh at me. But in this case, what we see is Rick and Morty, and you just have to click on these missecs, on these faces. In this case, you just click on these faces, and did anyone see the approval dialog of accessibility so far? Nope, right? But what actually happened is that we played the game, we were very good, we clicked 3 times. What actually happened is that in the background, we had the accessibility dialog. So every time we were clicking and enjoying the game, we just approved the capabilities. So just to close the loop, the meaning from that very moment, without known exclusions, is that when I go to other apps like Gmail, like my secure container, like my bank, and I just perform actions like write a sensitive email to my CEO, I'm sure everything is confidential, it's separated from the other apps, it's well written, Google is doing a great job. And I would just move forward. Needless to say, while I was actually sending this email, someone catched everything I'm doing. So now opening the other app, it's no longer a game. It's actually showing me everything I did on the device. So even if I meant to send something bad to my CEO, and I was just deleting it and writing again a new message, the app can see even the deletions and the changes that have occurred and the CEO doesn't even see. So just a quick demonstration about that. For those of you that noticed, this was actually, this was a demonstration on Android 4, and for many, by many, it was perceived as a problem that cannot affect Android 5. The reason is that the developers of Android have defined a policy that says that they allow the clickjacking to happen, but for the OK button, which is the last button in the process of approving the capabilities, they do not allow another layer to cover the button. So assumably, it actually circumvented the ability to exploit that problem. But at some point, we noticed that there is something very simple that can be done. That's the following. doing the exact same attack, but instead of just fully covering the OK button, leave a small hole and just get the user to click on it. The moment he does so, nobody is covering the OK button, and he can fulfill the attack very easily. So today, this is actually perceived and acknowledged by Google as a logical flaw, meaning it's a bad side of a very important feature, and there is no currently plan to fix this for Android 2 till 5, including, but in Android 6, there are a set of changes in the operating systems that make this kind of exploits not likely. So today, over 95% of population is affected by these kind of problems. Okay, so this was a very quick overview about some of the evolution and an example of the kind of things we foresee is becoming a very major threat and a tool to be used by attackers. But now I want to use the time that we have left to actually cover 3 families of approaches. Signatures, I will not spend much time on that. Dynamic analysis and static analysis. And then we will discuss in parallel what are the limitations of these kind of approaches to identify malicious activity. So around signatures, not much to be said. A concept that has been around for about 30 years, even maybe more. And when done properly, it's actually pretty accurate. But as we all know, the problem with signatures is that by changing, performing a mild change in an app, you can bypass a signature by an antivirus. So it's a very inherent limitation. And for that reason, dynamic analysis and static analysis have been developed over the years to try to identify more sophisticated patterns. So when it comes to dynamic analysis, again, the concept is to try to take an app, execute it, run it, try to operate it, and look at what it's doing in practice. The changes it does, the communication it does, and try to deduce that something bad is happening with the app. And the big problem about dynamic analysis is that it has to execute something bad in order to deduce something bad happened. That's exactly the kind of place where attackers are putting their focus in order to evade these technologies. So there are many, many, many concepts that have been defined over the years, but many of them are around time bombs or action bombs or IP bombs. And the notion says, if I now see that the IP where the app is being run is actually in Amazon IP range, maybe it's someone that tests me, I will not perform the malicious activity. In some other cases, I will define malicious logic like taking your contacts and calendar and stuff like that only after the 3rd level of a game. So a computer is not likely to play the game, succeed to get to the 3rd level, and then see that something bad is happening. And the last element is obviously the problem of generic techniques to identify a virtual machine. Malicious logic will run on a device, but will not really like to be run on a VM. Many, many techniques are to identify that. There are the known techniques of just identifying technically that you are in a VM. Other techniques talk about trying to see if there is a real human being using the device. So sometimes we saw technologies that did a lot of work on the technical level to hide the fact that they are a virtual machine. But when you look for the contacts or the calendar or stuff like that, you can see that there is a machine here. It's not a human being using the device. Okay, when it comes to static analysis, the notion is take an app, try to unpack it, sometimes reverse it, and then analyze the code itself to identify something bad happening. In here, the advantage of this approach is that it is not being run. So if an attacker wants to evade someone, it is becoming a bit harder for him as it's not running. He cannot identify the differentiation between a machine analyzing it and a user trying to use it. So just a quick overview about some of the fundamentals of static analysis. One of the most obvious things that this kind of analysis do is something called taint analysis, trying to show if data is being leaked to sensitive resources and stuff like that. So the idea is the following. Given this kind of simplistic code, is to try to move and see how the data moves from sensitive APIs, let's say taking your calendar for the coming month, and see if it's propagating into a sensitive API, like an API that sends information outside of the device. So this is obviously a very simple scenario, but the idea is that the sensitive API that contains sensitive data is usually called a source, and the API that leaks out information or performs something that is of a concern if it gets sensitive information is a sink. That's a very powerful capability. Over the years, a lot of technology has been invented around that, but there's a few problems, but one major problem with this technology, and that's a challenge of trade-offs between being accurate and between making mistakes. And I want to illustrate this very fast. So let's say that we've created an engine that maps all the sources, all the APIs that we want to look at, and all the things, all the APIs that we don't want to get sensitive information. The problem is that when things become more complicated, let's say that we see that information gets to some cell in an array, and at a later stage we see this array is feeding into a sink, the big question is, what happens if the sensitive information got to the first cell and then the information is collected from the third cell? So in this case, there is no real propagation of data, but statically you cannot always know about it because the index of the array is actually dynamic, so you cannot deduce it. So you have to decide if you won about this flow of data or not. That's the false positive and false negative trade-off. So there are many, many examples for very, very simple tricks to bypass static analysis. I want to show a very simple example here. In here, you can see a simple code. If you look at it, you can see that there is no direct propagation from data, which contains sensitive data, to data 2, which is used in order to send information outside of the device. But if you look at this very simple code, you can see that there is actually a copy logic from data to data 2, right? If the char is A, so put A on that cell. So in this case, there is no concrete propagation, even though logically there is a leakage of information. And obviously, the second element, which we will dive into in a few moments, is again the notion of making sure that the static analyzer does not have even access to the malicious code. That is done by using reflection or by just loading malicious logic dynamically when the app is executed. So statically, you do not have the data. In many cases, we think about dynamic loading of APKs, which is a common technique in real-world malicious apps, but there is actually another variation, which is hybrid apps. Think about PhoneGap or other frameworks that combine between native code and HTML together. So the HTML might operate native capabilities, but the HTML is loaded when the app is used, and it can be changed dynamically. So it's an inherent logical problem. So what the attacker really wants to do is to create an app that, when analyzed in an analyzer, will respond with naive and legitimate code, but when it gets to the victims, will load malicious code. And I want to use the next few minutes to actually show you on stage how that can be done. Okay? So what we're going to do is actually take a game, a popular legitimate app, and we are going to repackage it with malicious logic. And that's actually, based on research, represents about 60% of successful malicious attacks. Why is this so popular? Because, as mentioned, today there is a challenge of accessibility between the malicious writers and the victims. They get their malicious apps to third-party sources, which are in many cases less popular. So they have to use the human factor. They have to lure us as victims to download maybe a popular game for free, but also get their malicious payload inside of that. So that's the motivation. Okay. So the first thing I want to show you is actually this device, and the app that we are going to play with is actually AA. It's a very, very lightweight and nice game. I recommend you to play with it. So this is a live game. Okay, we're playing it. I'm very good, at least in the first stage. So now what we want to do is actually take that app and repackage it. Okay. Okay. So by the way, can you see the code? Yeah, it's big enough. Okay. So the first step we want to do is actually generate developer keys in order to be used in order to unpack and resign the app after we will do some changes. So now we generate the keys using standard tools. Now we are using APK tool, which is an open source tool, in order to take the APK, the new game, and just unpack it, open it in order to have all of the resources of the app. Okay? So what we want to do now is actually, just a moment. What we're looking in here is the manifest file, and that's actually setting the configurations of the new app. And what we will want to do is to actually insert new permissions into the manifest file. And we will also want to inject our code into the code, right? We want to insert new kind of activity that will actually load an APK from the server and just run it dynamically in the app. Okay, so in here we can see the class that is the entry of the code. Okay. What we're going to do now is to look at the SMALI and the intermediate code of that app. Okay. And what we are doing now is actually I'm going to show you where I'm going to patch the code. Okay. So this is the onCreate method. It's the method that is called when we open the app. So what we will actually want to do is to just inject a new method that will be called when this method is being initiated. Okay? So for simplicity, what we did now is actually use the Python script that added to the manifest file and permissions and performed the relevant changes to the code. I'll just show it to you very, very fast. It's a very simple change. So what actually happened here is that we inserted the new invocation for a new method that we've just inserted. Okay? The next step would be to just build back the APK. And in a few moments when we will conclude, we will actually have a new APK. In a moment we will sign as well, that can be used and distributed wherever we want to distribute it. Okay? So this is taking a few moments. In the meanwhile, I want to show you that we will create a new code that will be hosted by a server and feeded to the app. So in this case, I'm going to add a new message, and where we're going to compile it. Okay? While we're compiling this, I'm going to also set up a server that in this case will also feed the APKs from the server to the app, and also later on show us what are the ramifications of that attack. In addition, what we're doing now is actually using the developers' certificates in order to sign the app and make it ready for being used. So what I'm doing now is actually pushing the new app, the new AA app, back to the device, okay? And I'm putting the new APK to be available by the malicious server, okay? So in this case, what we're doing is actually loading a new APK when the AA game runs that does not do anything bad except of just showing us, hello, OWASP, I am benign, okay? And we can say that the APK was loaded. So far, if I'm now in analyzer, a dynamic analyzer, the code is working as expected. Nothing malicious is happening, okay? The interesting part is that we now can go and create another APK that what it will do is actually collect the last calls, meetings, contacts, very simple code that just accesses the information on your device, okay? And leaks it back to the server. So let's see what happens now. So in this case, I'm copying the new APK. And all that we're going to do is to just run the game again, okay? The game is running. I can keep on playing it. Everything behaves exactly the same. But as you may have noticed, the contacts, the last calls, the meetings have been leaked. So this is just an example of, in about 6 to 7 minutes, how you can just generate a new app, looks the same, but is malicious in a dynamic manner. Okay, so some of you, while I was presenting, were thinking, wait a minute, there is one server, some kind of a CNC, that can be blacklisted. I mean, many solutions, what they do, is try to analyze statically and dynamically what are the servers the app is contacting, and then deduce if there is a blacklisted malicious server. And one of the concepts around that is that an attacker does not have to rely on a specific malicious server, right? In many attacks, we see these CNC servers changing all the time, but again, they can be easily blacklisted. And the notion of trying to use social networks is actually an interesting notion. Imagine an app that what it does is actually accessing a new profile in a social network, like a new Twitter account. And what it does is actually look at new tweets and maybe try to load them as binary code. So most of the time, it does nothing bad. It just fails and nothing happens. And the exception is caught. But let's imagine that at some point the attacker want to attack. He can just insert a new tweet or a new Facebook message or anything like that that will be translated into code by the app. That is a dynamic logic that, again, relies on legitimate, popular, and public services. So we don't have much time, but I want to cover a few more topics. First one, this presentation is a bit depressing. We talk about the bad things that attackers can do. We talk about the limitations of the classical approaches. And the important element here is to remember that the classical approaches are great. They're covering a lot of malicious activity detection, but they are not all that can be done. And I just want to mention a few approaches that we really believe in as the future of identifying malicious apps. Okay? First of all, looking at the app itself is to some extent a mistake, because if you think about mobile attacks, there is actually a flow of attack, right? There is the app itself that is the result of the attack, but there is also the developers that created it, the sources it came from, etc. And we really believe that by being able to define who are legitimate developers and who are bad developers, what are the patterns of malicious activity developers, what are the toolkits that are popular, you can actually cover much more of the pie. In addition to that, we really believe that using crowdwisdom, using the insight that you have about a lot of applications, can really help in order to create better models about legitimate behavior and obviously bad behavior. And I would like to summarize and say that when we think about recommendations, it's always a funny part in the presentation, right? Because what I'm going to talk about is obvious. I think that most of us understand it. But when I think in the broader sense of things, I believe that we should be able to properly communicate to our colleagues and sometimes employees that mobile devices are a computer. And as such, we must be able to use the right tools and also the right education in order to make sure that attacks are mitigated and limited. Yeah. So obviously, make sure that you download from legitimate sources, educate your employees, be cautious about new apps that you install, and also make sure that you're running the latest software. It can be the OS, it can be the apps that you use. We see these trends are being exploited by attackers today. And last element, if you think about this as from an enterprise perspective, there are tools in the market today that are able to identify and protect your devices against a variety of attacks. That's very useful. Before I conclude, I just want to mention something that I found very, very interesting. It's actually coming from another family of threats. Because if you think about the threats in mobility, they are similar to some extent to computers, but a bit different. You can think about physical threats, having your device stolen or lost. You can think about network-based attacks, attacks on your devices from the networks around you. You can think about malware, and you can also think about vulnerabilities. And I want to share with you a slide that actually we created more than a year ago. It was an estimation, an attempt to estimate the number of security holes in iOS over the years. So what we did is actually take public information about the number of publicly known security holes in iOS that were identified and patched by Apple, obviously a subset of the real number of security holes. And we did it in April 2015, so we tried to extrapolate and say how will the year end. Do you guys want to guess how it ended? So as you can assume, we were totally wrong. This is how it ended. And I find it as an amazing stat as what it means to me. You can talk about it a lot, but for me it's one word. It's focus. Shift of focus by attackers and researchers from the classical computers to the new breed of computers. Guys, thank you very much for your time. Thank you. Any questions? Yeah. Yeah, so this is OWASP, so I cannot. Yes, the question is which endpoint protection solution would I advise? So there are a few in the market. SkyQ is one of the leading vendors, but I would not like to explain more. We can do it maybe one-on-one. Any other questions? Okay, thank you very much.